presenting the entire screen. Share. Okay. Let's hide this. Okay, so today we are going to cover together the course CEN 543. Where is this text box? So this is our course, Digital Image Processing. I'm choosing to use the monitor here of the PowerPoint rather than the board. This is cleaner. And so we'll cover digital image processing course together. And the most relevant information is the name of your lecturer. So I'll be teaching this course. And then the textbook, textbook, it will be digital. It's a traditional digital image processing written by Gonzalez. So Gonzalez. The latest edition that this book has come out is a 4th edition. It's really a good one, and it's the professor who wrote this book is a very nice person. So if you ever have any question about the textbook, he's very fast to receive. Of course, after he receives your comments or on anything on the textbook, he's also very fast into replying you back. So I strongly suggest to go over this textbook. It's very well written, and probably I could also share. Let me check for a moment. So the book, it looks something like this. Let's say Amazon.com. Image processing, or I can write here. Image processing, Gonzalez. Okay, so the textbook, I think, I thought the 4th edition has another paperback version, but the one apparently, so we're going to use this textbook, Gonzalez, the 4th edition. This has been around for at least 40 years. Okay, apparently we can even read it from here. For around 40 years, this book has been around, starting from the 1st and 2nd edition. And the same author has also a very good book that is image processing using MATLAB. I would strongly suggest, one second, this is image processing using, let me see if I can find this book, image processing using MATLAB. Yeah. So this is another textbook, which is also good, and you can use this as a reference if you want to implement or to test several algorithms that you want to on image processing. You can implement them using. You can use this nice book. Wait a second. Yeah, I cannot. So in principle, this is all the textbook that we need to go, that we are going to cover this semester. Digital image processing. I can put this link also here, while it's not very essential because it's very easy to track the textbook just by using this much information whenever you search this one. This textbook is in the library, so you can borrow it. It has different periods of that you can borrow for 2 weeks or 1 month, etc. It's good to have it, but you can also Let me say this. So the library, the book that you can obtain from the library, it might be a good choice on how to deal with finding the textbook. Now, in this course, we are planning to have, for the moment, we will have homeworks, and the homeworks, they're expected to be at least 20%. Okay, homeworks. The number of homeworks, I'm not assigning now a fixed number. When I say fixed number, we could have 4 homeworks each by 5% or 5 homeworks by 4%. So this is something that we could be flexible overall. And we're going to have a project for this course. And this project, it will have a midterm stage project. It will have also another project, which will be in the final exam stage. And I want to have a final exam, which will be written. And this final exam in written form, it's going to be around 20%. Okay. So now, regarding the percentage among these two, so we expect here a 20% in the final, 20% homeworks. That makes a 40, and 60% will be distributed among the other 2 projects. So that's all I can say for the moment. In this course, we'll cover the theory on the image processing, and we're going to put also importance on implementing text box. Sorry. Okay, so we'll cover the theory here, but also it is important to implement the image processing techniques in any programming language. The book that we are going to use, it is very close, or at least it leads a lot to using the MATLAB, which is a very good programming language. But you can use any other language, such as Python or Java, even Java, or C, C++. You can use any programming language whenever you implement something, or whenever you submit the homeworks. So there is no constraint using this programming language or some other. So we'll try to focus a lot on the implementing of the solutions. And other than this, I guess I don't have much new information or general information, which is out of the knowledge that we can get from the textbook itself. Now, I think we can go over the slides. So image, it has been recorded at different levels and at different quality standards for a long time, and the earliest images that have been acquired, they have been as early, apparently, this image, which is here on figure 1.1, this was acquired or produced in 1921. So it is exactly 100 years. So a century ago, so we started with images that look like this. So this is, let me see. I was wondering whether the name of the boxer, I don't know if he's a boxer or a runner, but anyway, so it looks like exactly 100 years ago, this is what we were producing. And around 30 years ago, there have been several movies that were predicting the future. When I say predicting the future, you always have these sci-fi movies where they explain how the technology is going to be in the future. And it's interesting to go over these movies that were made, and to nowadays, actually, we're living this time, and this time we're living nowadays, it has been kind of predicted by several movies, and you can always go at those and see whether they predicted it right. Okay, so if 30 years ago they thought that 1 gigabyte was too much, now we are living in this era, and we can really say, well, this movie producer, he was really good at predicting how much technology in terms of information in general, and also in terms of how images, how videos, and how other aspects of data processing has evolved. Okay, so 100 years ago, this is how images looked like. And in 1922, apparently, we have another digital picture, which was made from a punched tape using the signals that crossed the Atlantic twice. Okay, so the Atlantic Ocean, it was passed after some technologies developments that were made earlier in the previous century, in the 20th century, and apparently they could transmit this image with very low loss, or maybe no loss, depending on how was the original quality of the image. And this image that we see here, it had 5 different levels of gray. Okay, with 5 different levels of gray, you can assume that you can, so let's say if this image, which is figure 1.2, if this is, you need to distinguish something from the brightest spot to the darkest spot, and these 5 levels of gray can be anything which starts from 0, which would be the darkest spot, and then you can have 0.2, 0.4, 0.6, and 0.8. This will make 5 levels. Now, if you want to scale this one from 0 to 1, that means that we'll have 0, 0, a quarter, a half, 0.5, 3 quarters, which is 0.75, and 1. So here we have 5 levels of gray from 0 to 1, with a difference between the subsequent levels of a quarter of a unit. Okay, so this is how this image was produced. And now we are going to see in this course that it is nowadays possible to use a larger number of levels of gray or of different shades, so that we can have a more gradual change of the intensity in an image. What we are going to see in this course is that there is a huge difference between the human perception, which we can perceive whether a certain amount of a certain number of different levels of grayscale, whether we can perceive those or not. That's a really important aspect. But machines, computers, they can pick up. They are much better than us in terms of really not predicting, or at least reading and telling the difference whether we have, let's say, 200 levels of gray or not. We cannot distinguish very well if we are down in the dark scale. So even if the pixel intensity in an 8-bit image, if it changes by, let's say, by some levels of gray, human perception is not that good at reading it. Computers can do it, but this is how it all started, with only 5 levels of gray. And since there are only 5 of those, it might be relatively easy for human perception to pick up little differences from the background, which in this case is black, up to the face of this individual, who looks like Lawrence, which is also white. Now, these are the notes we kept today. So we're going to talk here the original of digital image processing, examples of where image processing is used, and also what is very important is the imaging modalities. With imaging modalities, we mean the different image acquisition techniques that can be implemented. We're going to talk about the fundamental steps in image processing, components of an image processing unit, and these image processing units, what they have is that they have a mathematical apparatus. Of course, this is like a digital signal processing. In this case, if you might have taken, so traditional bachelor level courses can be like signal and systems, where the signal is continuous, and you can use analytical approaches to solving or analyzing the images that you might, the signal that you might be given. And these signals, they might often be expressed as a function of time, which of course is discrete, depending on what is your resolution when you acquire data in the time scale. But now in image processing, we are dealing with two-dimensional signals, and these are discrete because the images that we often see they are described as a composure from a large number of pixels, where each pixel, it composes of a small square, or let's call it small square, which has a certain level of gray. Now, and this mathematical apparatus, or the framework where we can apply the mathematical tools, you might be familiar if you have taken courses like signal and systems, and also other courses that might help the understanding of, or where there is an equivalence between those courses and what we are going to cover this semester, can be also DSP, or digital signal processing. Okay, let's continue. So here we see another cable picture. Sorry, this is another cable picture which was dated from 1929, and apparently now we have here 15 different levels of grayscale, and this is the image we have obtained. And at that time, the tapes were used, and the technology of tapes, actually, it has been used for a long time. But what I can add here, and actually when you say tape, I'm not sure if, for sure we're not using them now, but me personally, we have used tape for a long time, when I was at least in the early 90s, where the tapes could be something similar to the recording tapes, where we could record a song or something, some audio, or movies, which used to be the VHSs. Now, there are some research areas that they acquire images that have a very large volume. So, and these research groups that have very large volume of images, and an example of this can be the three-dimensional images of a stone, okay? Or a similar example can be the three-dimensional images that one can acquire when you do an MRI of the brain. So if you do an image of the brain, the image it is going to be three-dimensional, and if we care a lot about high spatial resolution, then the image, it will be very large. You can have a single image which is 500 megabyte. Okay, so a single image of 500 megabyte. But then if you need to acquire several images as a function of time, these research groups that have this kind of data input, or this high volume of the data input, what they use is tapes. I was surprised, but I was talking with a colleague a year ago, and he said to me, yes, I mean, that's the only way that they can save all this large volume of images. What is interesting is that these groups that need very high volume, or at least images that have a high, let's say, which is composed of hundreds of megabytes a single image, these groups traditionally, they are not from computer science, they are not from computer engineering, they are from other fields, where one of the most or one of the areas that needs a lot of image processing are the petroleum engineers. So petroleum engineers, they take three-dimensional images of stones, so they drill a very deep hole, and their objective is to figure out whether there is oil somewhere or not. So they just take out a lot of samples, and they do the analysis of these images. So they are the people that are really interested into getting high resolution of these pores, because the oil, it stands on stones, and these stones, if they are porous, they have the oil in there. So they really care about the very high resolution. And they are the people that, at least that I remember, they even when they acquire these images, they have been the first ones before computer scientists into trying to use high computational power for these huge images. I remember myself in around the year 2000, I had some colleagues that were working in petroleum engineering, and in those years, the graphic processing units, okay, or the GPUs, Carta Grafica, they were not as good as they are right now. Okay, we're talking about 20 years ago, and I had colleagues that they were discussing with each other. They are all petroleum engineers and applied mathematics, and they were discussing. Because they needed to buy a PC, a computer, and they had to decide what PC they were going to buy if the image was 200 pixels by 200 by 200. Okay, because the computational time of an image in the order of 200 by 200 by 200, they needed around 10 hours. Okay, now this is a language, this is a terminology used by them. Okay, para cá jargão in natura. So they have their own language, because they were using those, and you could criticize them, telling them, oh, you don't know, you can use a graphical card, etc. You can tell this now, but 20 years ago, really, even computer scientists, they were not using GPUs. NVIDIA, it was not as good as it is right now. And you can add some more arguments, but I was surprised at that time that they really were discussing, or they were buying a computer depending on the size of the image. If they needed an image which was 400 by 400 by 400, that was very difficult for them, and they were applying at the advanced computer centers or grid centers, where they buy time to use hundreds of CPUs at the same time. So those were the groups that were trying to solve the solution in this way. Nowadays, the evolvement of the use of the graphical processing units, it has improved the situation a lot. But I can add here that the use and the knowledge to use a GPU for these important aspects is a knowledge which is mostly within the computer science and computer engineers. And the other engineering fields, they are not very good at using these fast computing units very easily. Now, I might correct myself to some degree, because, but this example, I could have given this a few weeks later when we're going to cover some other aspects, but I can mention it also now. So what I can say is that it's really interesting, or it's very interesting, that sometimes some developments, even in computer engineering, they start from other areas where physicists have been maybe the pioneers of many new developments. actually the greatest development, but this is not very close within our time frame. The physicists are making huge developments into developing quantum computers, where they don't want to use bits of being 0 and 1, which is on and off, but they want to use quantum computing, which now the different 0 and 1 is not on and off, but it could be the polarization of light. So you can have a photon, a beam of photons, an unpolarized light, which is coming out from the sun. You can use a polarizer, and you can change the angle of the polarization 180 degrees. Imagine now, you can repoint in this direction, like this, like this, like this. You can pick up not on off 0 and 1, but you can pick up 180 degrees, different degrees of freedom from the polarization of light. Now we can leave this aside because this might take some more time into becoming easily used by different users. But what I've observed in the last 2 years or 1 year and a half is that physicists that work at CERN, at the border between Switzerland and Italy, there is a Center of Nuclear Research, which was established by Italians around 70 years ago, with collaboration from all around the world, even before the creation of European Union. So before European Union was created, there was another union, which was the researchers to do fundamental research. And what they do over there, their contribution in one sentence by CERN, by these physicists and a large number of engineers, is that they have developed very large libraries for deep learning algorithms that can be used also in images to be implemented on FPGAs. Okay, FPGAs, they are not the best solution to use for deep learning algorithms because they don't have memory. They have the memory problems. The CPUs are good. They have memory. The GPUs are very good because they have a lot of processors. You are not talking about dual core, quad core, and octa core, but you're talking for about 1,000 core, which is 3 orders of magnitude more. So instead of buying 1,000 computers, you just buy a GPU. And the deep learning algorithms, it was a very huge success into being able to run those on GPUs. Now, very recently, so 1 year and a half ago, you could find 2 or 3 papers which were discussing the translation of the codes from a GPU or the libraries from a GPU to run it on a FPGA. Now, if you search now, that number of 3 papers alone, and actually the fundamental paper that did it all initially, it's a very classical one. Now it became a classic in less than 2 years. Imagine how fast these things can move. But the major aspect that I can also repeat here is that the large volume of images or large volume of data set is not always among the computer engineers or computer scientists. Sometimes it's on the other fields. These other fields are not very good at picking up the technology as fast as computer scientists. But sometimes, like the last example I just mentioned, they can even pioneer the use of new hardware by implementing the incorporation of developed libraries, and which will make possible to use, let's say, as an example, to use the FPGA for deep learning algorithms. Now, we started all this nice discussion from this word tapes, because tapes is really something old, but for even nowadays, tapes are much better than external hard drives or internal hard drives, because they can store a larger amount of data or images. Okay, so we talked about the tapes. Now, here we have another picture, which is the first picture of the moon taken by the spacecraft Ranger 7, taken in July 31st, 1964. At 9:09 a.m. Eastern. What is this, EDT? European, no, I don't know what this EDT is. And apparently, so this was not the traditional space shuttle that sent people on the moon, but it was just a shuttle which was sending a robot and taking pictures. Now, this image, this is taken apparently 17 minutes before impacting. Now, what is relevant for us at this stage, of course, this is just an image, okay? It's the moon, fine. It's like you are taking the picture of the sand. But one thing that I can mention here is that at the image acquisition modalities, or the different techniques that can be used for image analysis, one of the major difference is the wavelength that can be used. When we take a figure for photography, we mainly use a visible range. which means that we can use light to shine onto an object, and the light reflects back, and that light we can form an image. Okay, that is the case. I believe this image is also using the visible range of the optical spectrum, because so let's remember just this one at this stage. And when you talk about the optical spectrum, the different wavelengths that can be used for imaging, they are anything from actually from gamma rays, X-rays, UVs, ultraviolet, up to radio waves. So it's something on the top scale we can see the energy of the, wait a second, this doesn't look correct. This is 10 to the power 0, energy of one photon. So gamma rays, they have a small wavelength. Radio waves, they have a larger wavelength. So from left to right, you can see the increasing wavelengths. And so for example, the visible range, which is like this white spot, this one, I don't know if we have any other more detailed, wait a second, no, oh, I thought we had. Okay, no, let's go back. So the visible, no, I believe we have some more information here. Okay, when we come here, we'll talk about it. But the visible range, which is shown in here, somewhere in the middle, when the energy of each photon is 1 electron volt, but we are not very good at reading these values in terms of the energy. We are better at knowing the relevance of the image acquisition technique or a different imaging modality based on the wavelength. Now, one thing that you should, or we could always try to remember is that if we want to see an object, it has, actually I'm going to draw, I'm drawing something. I know that during the class, you can pin on my camera and not on the shared material. And you can see this one, but I'm afraid when we record this one, this does not have the same, you won't see this one as good. But what I want to say here is that whenever we have an image, this has a parameter here, which we can call this y. This is another parameter, which we can call this one x. And this is the field of view, okay? This is the field of view. And when you say field of view, this is a terminology which is borrowed from microscopy. Now, we have completely two different domains, which are inverses of each other, where one of them is photography, the other one is microscopy. Photography, what it does demagnification, okay? Because you can pick up a huge building, which can be 50 meters, and you're going to project it down to an area, to a small chip, which is 4 millimeters by 4 millimeters, okay? So 50 meters, you project it down by demagnifying it, okay? By narrowing down the light coming from an object. This is photography. Microscopy is the opposite. It does not demagnify. It does not pick up a distance in the order of 50 meters and projecting it down to 5 millimeters, but it's going to pick something which is in the order of micrometers and blow it up into the order of millimeters. So photography and microscopy, they are inverses of each other. But the most important thing I can tell now regarding the imaging modalities is that the spatial resolution that we can observe, it is proportional to the wavelength, okay? Which means that the light, the frequency or the length scale of one, actually what is wavelength? Wavelength, it's called a wave. So this is one wavelength. Electronic engineers, they are better at understanding this information. But what we can say here is that a wave, it is associated, it has attached a mathematical apparatus or a tool, which in this case would be the electric field. And this electric field, it is maximum here. No, sorry, it will be 0 here, maximum here, 0 again, negative down here, and 0 here. So whenever the electric field does a full cycle, which is like a cosine or a sine, this is one wavelength. And now the distance in space in this axis, this is the wavelength, this is 2 wavelengths. And this size, this lambda, it will be strongly correlated with how much we can observe, okay? Now, Let's remember this now. Let's move a little further. So here we have different examples using different imaging modalities. The first scan is a bone scan. The second scan is positron emission tomography image, which is PET. I think that's positron, which is like the other particle, which is kind of equivalent to the electron. And here we have a signals loop and gamma radiation bright spot from Richter valve. Now, all of these scans they are taken using gamma ray, and what we can see here, or what is the most important thing that we can go after, is trying to associate the wavelength of a gamma ray. So if you go back, we see that the gamma ray, it has a very small wavelength. Okay, so having very small wavelength, this immediately means that we're going to have a high resolution. Let's go to another imaging modality. So here we have examples of X-ray imaging. So let's go back. X-ray imaging. Apparently, they have a shorter. Let me think. They have a longer wavelength. Okay, X-rays when compared to the gamma rays. If the wavelength is wait a second. If the wavelength is longer, that means the resolution is lower. Okay, because this one you can compare the same way. Like if you have a meter bar which has divisions of centimeters, you have a resolution down to a centimeter or maybe half a centimeter. But you can also have a ruler or a meter which has the smallest division as a millimeter. So that's all we're talking about. So smaller the wavelength. Now wavelength, you can consider this one as being equivalent to the smallest division on your meter. So here we have chest X-ray, aortic angiogram, which is the second image below the chest ray, head computational tomography, which is the bottom image here. We have the circuit board. So actually this circuit board, the technology has developed so well that in order to inspect it, whether some connections were done wrong, we may need to get very good images, and then we need to blow them up, because we are not very good at observing with precision. At least an average human cannot do it very well. Some people have special skills, but having 10 different connections in less than 5 millimeters, it's too much. And sometimes when we connect these pins, we're talking about electronic circuits, we may not see it. That's why we take an image and we try to blow it up. Here we have another images, and these images, they are acquired using UV light or ultraviolet imaging. So here, these are some examples. This is normal corn infected by smut, and this is another different images. And again, whenever we say that this is UV light, we just go back to the graph. We notice that ultraviolet violet light, it has a longer wavelength than X-rays. That means that lower resolution. Here, now we go to another domain. So we are moving slowly. So this is light microscopy. Whenever we talk about light microscopy, we're talking about optical images or visible light. So let's go back to this slide. Sorry, the slides don't have a number. This is the worst thing that can happen. Not the worst thing, but one of the worst possible things. Because even when you present, let me do this now because I can refer this for myself. Apply to all. I should have done this one. And I didn't get it. So we don't have a slide number yet. Slide number. Apply to all. Good luck to us. If we couldn't do it, forget it. I should do it some other time. So we saw images in the gamma rays region, X-rays, UV. Now we're talking about visible. Here is visible, and in Figure 1.9, we are using visible wavelength, which means that the colors that we see, they cover a spectrum something between the blue and the red. The blue is around 400 nanometers. The red is in the order of 700 nanometers. Okay, so there is an almost 100% difference. Now 100 is going to be something, so you can change really from around 400 nanometers to 800 nanometers, and we can still see something. Okay, I think humans can see up to 800 nanometers, which means that if we have an image, we have a microscope and we want to have a higher resolution, what we can do is that we don't use a white light, because white light is a mixture of all the colors that we can see, that humans can perceive. We don't use white light, but we can use red light. But the red light is 800 nanometers. To improve the resolution, we can use blue light. Okay, we can buy LEDs, LEDs that shine only in the blue regime, or let's say 400 nanometers. Once you do that, you get a twice higher resolution, which means that actually, regarding the exact values of resolution, we're going to talk about these. That means that we can have twice higher resolution switching from red to blue. These are microscopy images, but now I can ask you one question. So if the wavelength is in the order of, let's say, 600 nanometers, 600 nanometers, it is 600 or 6 times 10 to the power 2. 6 times 10 to the power 2 is 600. Nanometers is 10 to the power minus 9. So this is equal to 6 times 10 to the power minus 7. Okay. Now 6 times 10 to the power minus 7, it is equal to 60 times 10 to the power minus 6. Now, actually, this is the place where it's best if we do it like this. I can use a board, but we can also switch text box. So wavelength, this is equal to, sorry, this is a lambda, which is equal, I don't know how fast I might be into converting this one into a symbol. Okay, so this lambda, if it is 600 nanometers, this is equal to 600, and 600 is equal to 6 times 10 to the power 2, and the nanometer, it is 10 to the power minus 9. So this is all equal to, let's say, this will be equal to 60 times 10 to the power minus 6. 10 to the power minus 6, this is micrometer, okay? 10 to the power minus 6 is micro, so that means that this is equal to 60 microns, okay? Or we call it 60 microns, it's short, but we can also micrometer. So that means that a microscope, it operates using these wavelengths. But let me check if I don't do any mistake. No, we are good. So at this wavelength, that's the best that we can see. And now lambda wave length increase. I'm gonna draw here an increase. Okay, increase. This implies that the resolution decrease, and the wavelength decrease, we get the resolution increase. Increasing the resolution, this means that one can separate successfully two objects closer than 1 micron. Let me call it like this. So this is what this resolution issue is all about. Now let's move here. Wait a second. So this was microscopy. You can see what we are seeing. Apparently, we can see the cholesterol. So cholesterol is a huge construct. Multiplying by 50 times, we can see it. We have an anti-cancer agent, which is multiplied 250 times. So magnification is 250. Then we see image C. This is a microprocessor, which is seen by a magnification of 60 times. We have a nickel oxide thin film, 600 times magnification. The surface of an audio CD, if we magnify it by 1,750 times, that's what we see. Organic superconductor, 400 times X. So 450x, that means a magnification of that order. Here we see some satellite images of the Washington, D.C. area. Now at this stage, these images are not anymore visible range, but we are moving into larger wavelengths. Okay, so this is something which is important to a note to talk about, because initially there was this image taken of the moon, that was just before landing on the moon. That one, it was enough to have a visible range. But if you want to take a satellite image, that one is not using visible wavelength, wavelengths. Okay. Now, the different wavelengths that we were talking before a while, they are listed here. So let me think for a moment. The visible blue, but wait a second. I'm making a mistake, I believe. So we said that my calculations, I think they were wrong. Multiply by 10, divide by 10. Yeah, I was wrong here. This is Gabim's father. You could have corrected me. You should have corrected me. But what is my mistake? This is 10 to the power 2 times 10 to the power 9 minus 9. What is this equal to? This is 10 to the power minus 7. Okay, this is my mistake. 10 to the power minus 9, 10 to the power, yes. And then what we can do is that we can divide by 10 the 6, which makes 0.6. If we multiply by 10 the power, which is 10 to the power minus 6. Okay, now this is correct. So this is equal to, let's do it like this. This is equal to 0.6 microns or 0.6 micrometers. Okay, there was something wrong even when I was doing this on this calculation before a while. It is good that we correct this on time. So this wavelength, actually, I would never believe, yeah, I should have noticed this one much faster. I was a little confused, actually. So the wavelength 600 nanometers, that means that we have a resolution of 0.6 micrometers. So this is better. So microscopes at the optical visible range, they have a resolution better than 1 micrometer. Now, this corresponds to actually a hair thickness. Someone who has a good hair, this is approximately 30 to 40 micrometer. So this is how thick it's a hair. That means that it's very easy with an optical microscope to observe the hair, or let's say the thickness. Now it's getting darker. Okay, so sorry for this little mistake. Let's continue again. Yes, this is the resolution which we should obtain. And in fact, what happens is that these resolutions, this is, let's call it, this is half a micrometer, but things can get better. Resolution can get better using computational imaging. Now, there is a very amazing new field of research, which is computational imaging, and people are publishing here very actively because it's a really good area where they use different algorithms in order to overcome the physical limitations of a microscope or an image acquisition tool. So this uses, let's say, algorithms to, let's say, to overcome or to compensate for the physical limitations of an image acquisition tool. In this case, this could be a microscope, okay? And actually increasing the resolution, that's the place where we want the better resolution. We don't want a very high resolution if you are taking a picture of a mountain or something, unless you want to see, let's say, the hair or the fur of animals or something. So the resolution, it's what the physical, it's all related to the physical limitation of the system, which is strongly related with the wavelength, is strongly related with the quality of the lens that you are using. It also relates, so there are many aspects actually. Probably I can list a couple of those. So the resolution, it is a convolution of several aspects. Let's call it this way, of wavelength. That's the first one. Second, lens system. Now, lens system is we can also call this one light gathering system, because you don't even need a lens actually to acquire an image. And now with light gathering systems, I can also consider a pinhole. So let me call this one a pinhole. Before the lenses came out, in the very early stages of early Europe, people were using camera obscura, okay, to obtain an image or something. So these are some aspects. Another important aspect regarding the resolution is the quality of the CMOS. CMOS is a little the physical component that carries the pixels. CMOS, and this is related to the size of a single pixel. And nowadays, this pixels in the order of 1.1 micrometer, you can buy it for around 180 euro. So they are cheap. You can buy a small CMOS, which has, and this is difficult to make. Not difficult, but let's call it, this is something which increases the price of the component, okay? Let's call it this way. And let me think for a moment. So the CMOS that you can buy nowadays, there are components which are something, so let's say 2000, no, 19, I used to remember this, but it's not that essential. It can be 1056 times 2400 pixels square. And this means that if one pixel, it is in the order of 1.1 micrometer, that means that the pixels, the CMOS, it's something between 2 millimeter times 2 millimeter. This is the size of the component. Let's say if pixel equal to 1 micron. Now you can buy for much cheaper money, or for much for smaller amount of money. You can buy the same, let's say another CMOS that has pixel size around 3.5 micron. This is much easier to make and also much cheaper, and also increasing the size of the pixel from 1 micrometer to 3.5 micrometer. It has also some other benefits, because you always have trade-offs, because the signal to noise ratio, it is better. So if you have 1 micrometer pixel, the noise is higher, so you have to compete. If you have a low contrast, or let's say a very let's say low contrast or low quality image, it might be best to use a pixel, depending on the application, to use a pixel which is larger. Actually, so 1.1, it might seem like better. It's also very expensive, but sometimes you might have to, based on the trade-off that you have at hand, you might even go for a system like this. Now, all of these components that are listed here, they are all related to the hardware of the mathematical construct, or the hardware of the microscope, or of the system. Now, this has a certain limitation, but this limitation, it can be overcome using the algorithms or computational imaging. Anyway, so let's continue. But this is really a beautiful area of research, and you can find very good research groups working in this area. We are also doing some computational imaging in microscopy, and we have been using it for some time. And any one of the projects that someone in the class can pick can be using computational imaging to improve the resolution. Okay, so now we come back to the slide that really it was a reminder for me for the mistakes that we just made a few slides ago. Visible blue is something 0.4 to 0.5 micrometer. There's a wavelength, and it's used for this type of imaging. We can go to the visible range, which is visible green, the green that we see. It's a higher wavelength. We notice that the red color is around 0.7 micrometer, which is 700 nanometer. Then we go into the infrared, middle infrared, thermal infrared. So we can go in the order to 2 to 3 micrometer large wavelength. And this directly relates with the spatial resolution of an imaging modality. So here, this is an image of Hurricane Katrina in 2005, a very sad day when Hurricane Katrina approached the coast of US. And this image, it is taken by using a multimodality, using both visible and infrared wavelengths. And this is what we obtain. Now here, this is again another image taken during the night, satellite image, using something between 10 to 13.4 micrometers, which is the infrared range. We have other images. Okay, this is all about the imaging modalities, and these are some areas that can be used in technology, where image analysis is essential to check the quality of the products that are produced. The first image is circuit board controller. So you take a very high quality image, and really a person cannot see with details whether the connection on a circuit are done correctly. Okay. We have in our electronics lab, actually, sometimes we have to connect very small components on very small chips on some circuits that we need to produce at times. And you need to use a lens, a huge lens, a very good lens, in order to really see what you are connecting. Otherwise, it's impossible. So these are some examples where you can use to see what is going on. You can also check the air bubbles in a plastic product. So sometimes you want to make a good plastic bottle, but you have some air bubbles. It doesn't look good. Yeah, it's good to have a high quality of material, etc. Here we have some other images in the visible spectrum. We are used to these because these are all visible range. Okay, this is like photography. This is a red spaceborne radar image of a region in Tibet. This is something wavelength used here is in the order of 10 micrometer. These are some MRI images, magnetic resonance imaging of a human knee and the human spine. Images of a stellar construct. Now we are moving into space, and so we use gamma. So it's the same object we want to observe, and we try to pick it up with gamma ray, with X-ray, optical, infrared, and radio, and we notice that the wait a second, the center covering there. And as a function of wavelength, we can figure out, or we can look at and decide which wavelength is the most appropriate to pick up this Crab pulsar, which is a stellar constellation. Now, these are images of a seismic model. These are just another image. This is ultrasound images, which are very common nowadays. A few decades ago, you could not easily get one of these. And this shows, and this is the top one. It's the ultrasound images. The bottom ones is the image of thyroids and the muscle layers images. Here we go to another a very high resolution so this is nothing like a microscope. This is a microscope, but it's not using light. It is using electron beams. Now, this is a SEM image, SEM, which is a magnification of 250 times. This is a huge development because the wavelength because now you have a photon. Photons, even if you are not very good engineers, we might have heard that photons have no mass. No mass. Mass are zero. The mass is zero. But electrons, they have an experimentally measurable mass. Okay, so these objects that have an experimentally measurable mass, the wavelength is much smaller. If the wavelength is much smaller, the resolution is much higher. Okay, now what one can do, not we and everyone, is we can try to buy a laser source or a light source which is shorter wavelength. So we don't always need to use a visible range, but because visible range, we said it was something between 400 and 800 nanometers, but we can buy a wavelength which is in the order of 20 nanometers. Few months ago, Professor Julian told me, Arban said there was a light source which is 50 nanometers. It might be good to buy it. I said, okay, let's have a look into it. And but it was high intensity, and the price of that light source, it was a laser source using 15 nanometer of wavelength. It was €1 million. Okay, so that's the price that you might pay only for this wavelength. So it's very easy to produce a laser source in the visible range. You can buy for €10 or €5 a laser pointer to show the slides when we have a presentation, to show the components in the slide. But once the wavelengths drop to in the order of 10 nanometers, the price increases too much, or let's say a lot. Okay, so these are some other images, and now overall, what we can say is that in this course, the information that we'll try to cover is that in the chapter 2, we are going to talk about image acquisition a little more in detail. And especially this chapter, I love it personally, image acquisition, because it's really good to have a good knowledge on both the hardware and also knowing also the different imaging modalities, how they operate. There is really very good techniques, very good engineering knowledge, which is not very difficult, and it's good to cover it, okay? Because once we understand the principles that image acquisition tools operate, it is also very easy for a user to know what type of noise filtering one has to use. Sometimes some image modalities, they have, let's say, for example, they have Lorentzian noise, okay? So once you know that you have the type of your imaging modality, you say, okay, the noise is going to be Lorentzian, so let's use filters that filter out the Lorentzian pixel distribution. That's good, so you can improve it based on your knowledge. I really love chapter 2, and we'll try to provide as much details as possible from this chapter 2. In chapter 3 and 4, we are going to talk about the image filtering and enhancement. So always when you acquire an image, because of many aspects like low contrast, low resolution, or bad image, let's say, or maybe there are some objects which are interfering, or there is, let's say, in principle, let's call it low contrast, non-equal illumination, or the illumination at different parts of the image can be different, which makes it difficult to analyze. So there are a lot of algorithms that we can use, which include image filtering and enhancement, in order to improve the quality of our image. Now, there are two aspects to this. We can improve the filtering and enhance an image to make it better for human perception, which means that we can see it, okay? But the same thing can be done, when I say it can be done, or the same thing, it will have a better effect also if we use computers to do something, which means that you can use deep learning to do object detection. And when you do an object detection or object counting or object classification, there is a pixel gradient distribution across an image or across the different components of the object that you want to observe, okay? And for a computer, even though we may say that they are better at quantitatively obtaining information, if they are better than humans, still image filtering or image preprocessing, it greatly improves also complex algorithms that can be run solely by a computer, okay? So it might improve, let's say you might have let's say, a classification algorithms between two different objects. Using specific image preprocessing tools, you might improve the accuracy by 10%, 5%. It always helps. Chapter 5, it talks about image restoration. We're going to talk about this aspect too. In chapter 6, we're going to talk about the wavelets and other image transforms, which can be used for the sole purpose of improving the image quality, trying to acquire as much as analysis out of a given image. Then chapter 7 is about color image processing. Chapter 8 is compression and watermarking. And I believe this is as much as we can cover in this semester. So we may go up to chapter 7 or 8 together. But I may strongly suggest, it depends on how we distribute the projects for the course, because I may choose, that's what I've done in the previous years, for some of you to do the, let's say, to do the projects using materials or topics from chapter 10 to 13. So it is not something which is very difficult. It can be done, okay? But we have to cover the first 7 chapters, because it teaches us how to work with the pixel, how to use the convolution of different kernels in order to detect edges, in order to detect objects, so edges of a certain object, or how to detect the object as a whole. Now, these principles that we are going to learn in the first 7 chapters, they are directly implemented in chapters from 10 to 13. But as I said, we cannot cover all 13 chapters in one semester, because no university can do that unless it's a 2-semester course. So outputs of this process generally are image attributes. Okay. So this is how the semester is organized. Now, some examples that can be used in image analysis is, for example, the sound steganography, or how we can hide information, or how we can encode information into some other different modalities. Here, actually, we had some work which was published, where what we did is that we were trying to hide a specific image, and what we did, we had an image, we divided into 8 different components, and these 8 different components of the image, we hide them inside 8 different audio files. So we embed those into these audio files, and a user can still listen to the same audio file, but does not know that there is 1/8 of an image hidden into these audio files. And now these 8 different audio files, what one can do is that you can distribute this one to 8 different people, individuals. And then what is the objective? The objective would be to pick up the original image. And this original image, what we did, it was divided into 8 different pieces, which you can understand nothing from those. You can then embed these images, or portions of these images, you can embed them onto audio files, give them to 8 different individuals, and then you can pick up only 5 individuals out of these 8. You can get 5 audio files. From these 5 audio files, you can extract 5 portions of the original image, and you can reconstruct the image not from 8 different parts as we separated initially, but you can need only 5. And this is called like an algorithm which was developed by Adil Shamir, who is for secret sharing scheme. In one sentence, you can be like this. You have a code or password that you divide this password into 8 different parts. But if you want to get the password back, you don't need to get all these 8 people together. Randomly, you pick up 3 of those between these, and you can reconstruct the image. Now, often the image which is used a lot in image processing is this Lena image, which is shown here. We didn't use this. We used Hegel image because out of respect for him. And another thing that I wanted to note here is that we are in year 2021. We said at the beginning of this course that the earliest images, they were acquired 100 years ago, 1921, exactly 100 years. And in 1995, I remember when this movie came out, it was a very beautiful movie. It was very high-tech, hard to understand. And in that movie, it happens in year 2021, so it happens now. And according to this movie, information was everything. That was the first thing. I believe that many would agree with this. And transferring information, it was not secure. Also, we agree with this. And according to this movie, what they used to do to transfer information, they used to have humans or carrier that were transferring this information. So they would encrypt this information in the order of 320 gigabyte into the brain of people. And Keanu Reeves, before he became a star in the movie Matrix, which is also a sci-fi or high-tech movie, he played in this movie, Johnny Mnemonic. And this was the last time we saw Dolph Lundgren. Dolph Lundgren played in this movie after he played Rocky Balboa in the Rocky Balboa movies. He played in this Johnny Mnemonic, and he was back when he played Expendable with Sylvester Stallone. So it was a long time we didn't see him, but this was a time when he played with Keanu Reeves. And the reason I brought this back here is that in this movie they discuss how the information that they encrypted and decrypted into images. Okay, so this is how they explained it over there, which is very similar to what we try to explain in here. So information can be embedded into an image or into an audio. Then, in order for people not to find it easily, you can divide it in a large number of components. So here in this work that we published, we divided into 8. According to this movie of Johnny Mnemonic, they divided in 3 images. They encode it. They put it into the brain of Keanu Reeves or Johnny Mnemonic, and they transfer this data from one city to another. Now you can go over this movie if you want, and you can really check these numbers, and you can compare. But it looks like transferring some data in the order of 320 gigabyte in 1995, it was something huge. In 1995, in the newspaper, there was a question asked to Bill Gates, who is a respected individual nowadays, and they were asking, shall we make the memory of a computer in the order of 5 megabyte? He said, no, there is no need for that, because there is no company in the world who has more information than 5 megabyte, because back then it was all about something which you can store in an Excel sheet with data or the name of people, for example, for for health insurance. People, when they were paying their money, the records, it was very important to keep track of the data. In those years, the most difficult, complex thing that you could do with a computer was storing digitally the names, the birth dates of different individuals. And yeah, I can give more details about this one. There are very interesting stories which are told regarding these. But at that time, even Bill Gates was not very good into predicting correctly that one day companies might need a storage of higher than 5 megabytes. Okay, so but the sci-fi movies predicted it, and that's what they were trying to do. Now, overall, so this is some aspect that we are going to talk. In the end, we can say that a complete image processing unit, it has several components, and these components, they all might start with a computer, then image display, which is a monitor, hard copy of the images that we can acquire. We may need specialized image processing hardware. Then there are image sensors, image processing software, mass storage. Now, when you look at this picture, so I think specialized image processing hardware. So you look at one of these boxes. Now, what are these image processing hardwares? What could this be? Now, this could be small portable units where one can implement the solution and can run it. Okay, so now, and actually even this computer, I could choose to remove the word computer, and we can call this one computing unit. Okay, if we say computing unit, it is anything which includes a Raspberry Pi. So Raspberry Pi, it's a small portable unit, and it is always compared to a credit card because it is as large as a credit card. Where you can install operating systems, you can run, you can connect it to a camera. So this Raspberry Pi, it is half the size of a cell phone. You can store. Actually, we always give the example of Raspberry Pis, Arduinos, etc. Even our cell phones are computing units. Now, these cell phones are much better than computers that used to be 10 years ago. So in terms of they do filtering of the images. You take an image, you filter it out, you give different shades of gray or red or whatever you want to do. So this word of computer, you can substitute it with computing units. And here it can be anything between a Raspberry Pi, a GPU, an FPGA, and Jetson Nano, an interesting unit or component, a hardware component. It's also Jetson Nano. Jetson Nano, it's a product which is made by NVIDIA. So assuming that NVIDIA, it's a company that makes thousands of processors into a single unit, is the same thing that's carrying thousands of computers in your pocket. Jetson Nano, produced by NVIDIA, is also a very powerful hardware, or let's call it, which can substitute a computer for any specific reasons or for any specific application that one may be interested into using. Now, one thing which is very common, or people try to do a lot, is the following. What you can do, or what one can do, is that you can acquire a data set, and you can use deep learning algorithm to train for training. And this training could include classification of objects or object counting to do object detection. And once you train it, the file that is going to carry all the weights of this process, it ranges something from 20 megabytes up to 500 megabyte. Now, having 500 megabyte, it's something which is very heavy. To store it into a portable unit, we tried it with our students last year, students that were in the Master of Science study program, and it will be great if you also do a similar project. So we trained the model for object detection. It was for microscopy. The weights, it was a huge file, 0.5 GB. We put it on a Raspberry Pi, and then on this Raspberry Pi, we inserted a new image, microscopy image, and we were asking the Raspberry Pi to read the model and run it, but apparently there was not enough memory into that little thing. Okay, maybe it needed a higher RAM. The RAM that it had, it was 4 GB. Probably this 4 GB of RAM could have been the threshold of really being able to run smoothly, reading a model that is trained, which are these HDF5 files. Maybe it was not powerful enough to read the trained model and to run it and to test it on an image that we are going to insert it later on. Okay, probably Raspberry Pi could not do it. Most probably a Jetson Nano can do it. Allow me just 1 second. I want to double check one little thing. Chrome. Can you listen to me? Can somebody confirm whether you are listening or not?
Yes.
Okay. You are back. Okay, so yeah. First of all, after some time, it just came to my mind that I might have to check whether we are recording. That's the first thing, and second thing, whether we are listening, because sometimes the fluctuation in the So now we're talking about these components of a general purpose image processing system. I was saying that sometimes some computing units might really be running at the given parameters that you can buy them nowadays. They might be just at the threshold between doing what you are asking them to do and not doing it at all. So in this case, I just gave an example of Raspberry Pis not being able to do that, but probably a Jetson Nano, which is a product from the family of NVIDIA, probably can do it, and it's a good thing to test actually all of these solutions, whether we can run them or not. So I just wanted to say this word computer, we can substitute it with imaging, let's say with computing units. Mass storage, I think we know it. Probably this mass storage can be anything like a hard drive, SSD or HDD, and even a tape. Okay, even 2 years ago, I never thought that people are using tapes nowadays for image storage. Apparently, they do. You can find them on Amazon, and they were not very expensive, but you need to know how to use them, etc. Image processing softwares, I think we commonly know what they are. Specialized image processing hardware. Now, specialized image processing hardware, I believe that GPUs maybe could be a good example of developing of hardware. FPGAs are also very nicely built up hardware components, which are specially made and which are also need to specifically be programmed in a way to run an algorithm or to run something on an FPGA. Okay, so then we have image display. Image display, we have nothing about it. It's just a monitor or some portable monitors. Nowadays, a lot of these little components, it doesn't have to be a PC monitor. It can be this portable displays, which are anything from 5-inch to 7-inch diagonal of the monitor or of the screen. Okay, so this is all that I wanted to talk about in the first week. So during this semester, this is all that we want to cover. As we said, we try to cover anything, the first 7 chapters, but the projects, they can be assigned from the later chapters in the textbook. Do you have any question? Stop recording.